Hi, I'm Subhan Ahmed, and this is my peer Adythia. And the research we're going to be presenting is disease detection from just X-ray images using deep learning. We performed this research under our professor Ole Fosberg, and we used the Richter Memorial Fund to conduct this research. So the main problem that we try to solve was that can AI detect disease from just a simple chest X-ray image, as we can see over here?
Based on a literature review, the first literature review, we saw that there were like many images trained on the dense net model, and one of our literature review suggested that it surpassed their average radiologist performance in detecting pneumonia, and it achieved a F1 score of 0.435, which means that the higher they had a, like higher true positives, and as compared to the average radiologist, which was lower of F1 score. And also it used like camps like activation maps to provide a visual explanation for predictions. So as you can see here, this is an example of grad camp which highlights the region where uh, it suggests where pneumonia has been detected a lot. So the more the like the redder regions, it suggests a better suggestion for pneumonia. And what we did was we added two data sets. So one was from the NIH chest X-ray dataset, and also we used the Kaggle pneumonia dataset, which was from the Guganso Medical Center from China. And with that, we integrated GradCam to just see where which areas had a lot of pneumonia detection with red regions, not just to explain the prediction, also to give a more uh, information of like misclassified cases. Next. So, uh, our research question was how our machine learning model can accurately detect to classify X-rays into normal or pneumonia. So we divided our data set into training data set and validation data set. So we also divided the pictures into like a train and with the validation split of 30%, and which we subsetted as training, so that we know what we are which batch of data set we are training first. And and we are also giving a image size of 224, like 224 for all the images. And same thing with the validation, we are also mentioning the subset validation to just give a better information with what we are using for training and validation data set. And again, we use a validation split of point 0.3. So as I told before, so this was our NIH data set we used before. So this was a US based. So we wanted to see how like different data sets perform with our machine learning model. So what we did was we defined the path first for the NIH data set. Then later on, we uh, we had a CSV file which had the labels of all the diseases, not just pneumonia or normal. We had different other diseases, but our aim was only to detect normal and pneumonia. So what we did was we checked all unique labels for first, and whatever unique labels we had, we removed, and we just kept pneumonia and like normal images. So yeah, to better make our model machine learning model better. So yeah, as I explained before, we uh, we we uh, searched whether we had the pneumonia normal images, and we found like two. I think we had like many normal images. So what we did was to normalize both the pneumonia normal images. We reduce the normal images size to, I think, 2500 to like to match the pneumonia images.
So for the piece processing, so the way we like process the image so it can be like further fed into our model was that we first like read the image path, and then we decoded the image using like the three image channels like RGB, their color depth, and we made sure that this the image size was 224 by 224, and then we converted that size into like a value which was between 0 to 1, so we can like normalize it, and then we return the image and the label. And then after that we made this whole training data set using our tensor slices, using the paths and the labels, and then we basically mapped the each images into the training data set, and we made sure that each batch was like consisted of like was of like 32. And so this mainly like consisted of like us like resizing and normalizing, and just making sure that we had like balanced classes. So our model architecture was basically uh, a dense net model. So a dense net model is basically like a pre-trained CNN model on image data. And so firstly, we can see like base model dot trainable is equals to false, means that we're using an existing model and removing its final layer, so we can make our own final output. And it could be like even more than like a just like a binary output. It doesn't have to be like either pneumonia or like uh, normal. We could add like multiple other diseases as well, but for now we're just working with pneumonia. And so this is our like basic model architecture, which consists of the base model, and then we're adding this global average pooling 2D, which basically converts like a 2D the features from 2D array to 1D array. And then we're adding like another dense net layer with 128 neurons using the ReLU activation function. And then after that, we're dropping out like 50% of like neurons to make the whole thing more efficient. And then finally, this is our output layer consisting of one neuron, and using the sigmoid function to finally give a classification. And we can see the whole pathway over here. And then for like our model training and our classification, we use the binary cross entropy loss, because we just had like two outputs, either it's pneumonia or it's normal. So that's the reason we chose our binary cross entropy loss, and the optimizer was Adam. And in case our model became constant or was giving like really good accuracy, in that case we would like stop early, and then we just adjusted some class weights. So we can see over here that we're using accuracy, binary cross entropy, Adam, and then we're using like 30 epochs, which basically means that like the whole model will train on the whole data set 30 times. It will like, go through the data set the data set 30 times each. And then this was our results for like the Kaggle model, the data we got from like the China. And so we can see that like this model was like performing really well. We had like our confusion matrix, which showed like it predicted like 153 labels correctly, whereas it correctly like identified uh, 318 pneumonia cases. And it only like it was like uh, wrong in like 81 cases of normal, which it classified normal cases as pneumonia, and it only identified like 13 actual pneumonia cases as normal. And this is our ROC curve, receiver operating characteristic, and which shows that the AUC is basically 0.95, which is like pretty good. And the more the curve, this elbow is on the towards the top left, the more the good the model is. So we can see like it's pretty like up here towards 0.95, and we can like confidently say that this performs like really well. And so this is like a normal chest X-ray, and this person contains pneumonia, and our model was able to like correctly predict that this chest X-ray had pneumonia. And the grad cam on this image shows that which areas in particular were like really relevant in terms of identifying this image had pneumonia or not. And this is our classification report for the China dataset, and it showed that the whole thing achieved like an accuracy of 85% and did like pretty well than like an average radiologist. And then this is the result for our NIH model, the data from our NIH, the US data, and it showed that it performed good, like but not better than the China like data set. And the EUC value was 0.81, and relatively it did like pretty well in terms of like being in the top left side of the whole graph, and it was able to like predict 214 correct normal labels as well as 226 correct pneumonia labels. And then this model was also able to like identify this chest X-ray as pneumonia, and this was the grad cam it showed for the reasons it classified this image as pneumonia. And then the NIH model was able to achieve like an accuracy of 76%.
So this is our like analysis from this project, and also what we so like intend to do for our future work. So what we found is we found like a class imbalance in the NIH dataset. So we found like there were like a lot of normal images at first, and we had to like remove a lot of normal images, and also there were like also more pneumonia cases as well. And there were like noisy labels from the automated report extractions. So we found like since we found like many images which are supposed to be normal, and it detected as pneumonia in our NIH dataset, like NIH dataset. And what we thought is maybe like we could like tune the prediction threshold using the ROC slash F1 score to optimize clinical performance. And later on maybe we're thinking of just not to just stick with just pneumonia normal, and also look at other diseases which are like prevalent everywhere, for maybe like COVID-19 or other diseases as such. And we are also thinking to like integrate med gamma, so for like for the chest x-ray images. So basically med gamma is like you input a chest x-ray images, and it tells you all the analysis of that x-ray image, says what kind of diseases it has. And we can also keep questioning like about the image in like in every different way. And maybe also we could expand our data set, just not stick with the NIH and NIH data set on the China data set. Maybe like look into other data sets as well to have a better generalization. And then we could also like fine tune the model on the balanced data set for more improved reliability. And the conclusion is that we found out that the Kaggle dataset, the China dataset, performed better than the NIH dataset, because the NIH dataset was imbalanced and more noisy, and we were able to achieve a 85% accuracy on the validation dataset of the China dataset. And also we integrated GradCam for more model explainability. So we didn't just stick to whether the image is pneumonia normal. We just also wanted to show which areas of the chest X-ray images had uh, more more prone to pneumonia disease, and which is why it led to the result by the chest X-ray images is pneumonia. And also, yeah, as GradCam explained, which lung regions were more prone to pneumonia, which it also highlighted the areas where it had pneumonia. And what our model shows that the few like we our model also shows potential for AI assisted diagnosis in real world use cases, rather than to reduce time for the radiologists to make their own conclusions.
Thank you so much for like watching our presentation, and we would like love to connect with you if you want to like reach out to us. And so my email, if you want to like reach out to me, is subhan146r at gmail.com. I can spell it out for you. It's like subhan146r at gmail.com. And my friend Aditya will also like share his email if you want to like reach out to him as well.
Yeah, my email ID is ad aditya 4003 nms at gmail.com. So it's ADITHYA. That's my first name. Then 4003 nms at gmail.com. Thank you.
Thank you.